All right. So, what we're going to talk about today is just going to be a little bit more about some of the periodic trends that we started in our last discussion. And this should help a lot with prepping for your upcoming exam, covering up to the end of chapter 3. And so, we will talk about this again on Tuesday, but this is just a review for you here. And so, what we're going to be doing is the other day we finished talking about atomic size, and we're going to relate that to the size of ions and then continue talking about a couple more periodic trends. And, as part of that, I just want to review what we had talked about that was like the main component that determines how all of our periodic trends like act. And that was this idea of effective nuclear charge, which was the idea that all of the core electrons within an atom, meaning that those that are contained in a filled shell, or in another word, those that are in the noble gas configuration, what they do is they prevent electrical charge from the nucleus reaching our valence electrons, those that are on the highest energy level. So these would be our valence electrons. And when I say highest energy level, what I'm really talking about is those with the highest N value. So that could be things in the s or p type orbitals. And so if your inner electrons are going to be shielding that charge, we want to think about how much charge do these outer electrons receive. And we said that's this effective nuclear charge. And we get that by taking the number of protons in the nucleus and subtracting from that the number of core electrons, those that are shielding charge and preventing these outside electrons from feeling all of the nuclear charge. And if you want to think about it, you can also think about these shielding core electrons are those that are repulsing the outer electron. So that you can also think of this as electron-electron repulsion that is preventing you from seeing that positive charge. So you get the attraction from the nucleus and then the repulsion from the like charged electrons. So we did a calculation for this. We talked about sodium. It had a noble gas configuration of neon 3s1. And using that, we were able to figure out, three main things. One, when we found sodium, we saw that it had that Z value of 11. So that's our number of protons. Our number of core electrons is just whatever the elemental number of this guy in the noble gas configuration is, or you can just count out how many electrons are up in that electron configuration. 2 from 1s1, 2 from 2s2, 6 from 2p6. That totals to give you 10. And we said that when we calculate the Z effective, we take our number of protons, we subtract from that our number of core or shielding electrons, and we got this plus 1. And we said that the one valence electron for sodium, that one that's outside of the noble gas configuration, receives a positive charge of plus 1 from the nucleus. Then we talked about how we can look at the Z effective, and there's a trend or a predictable behavior for those atoms as we go across the periodic table. Z effective increases as you go from left to right and remains constant as you go from bottom to top, based off the fact that as you go bottom to top, you have the same number of valence electrons, and each one of those feel the same Z effective. And then as you go left to right, you have the same noble gas configuration, same noble gas, but more protons in the nucleus. So more P plus in the nucleus. And so that was our trend with Z effective. We then said that you can utilize Z effective to think about any trends in atomic radius, where we said that atomic radius depends on two things. First, the size of the largest orbital, so those that have the largest principal quantum number. And that's going to matter when we go up and down a column. And then second, the other factor that determines our atomic radius is that these largest orbitals get smaller with greater Z effective. So the larger that value for Z effective, the more attraction you have between the nucleus and your outer valence electrons. And so you have some compaction of that orbital as you go from left to right. And so we said that left to right, higher Z effective is the dominant thing that's affecting your size. Up to down, it's all about your change in N. Because we have, for hydrogen, that's N equals 1. Lithium starts the N equals 2. Sodium N equals 3. Potassium N equals 4. Rubidium N equals 5. Cesium N equals 6. Francium N equals 7. So as we go up and down, we're just getting those higher energy orbitals. We talked about how you measure atomic radius. It's just the distance between two of these atoms that are bound together. You measure that from nucleus to nucleus, and then you take half that distance to say what the radius of each given atom is. Now, what we're going to talk about is the radius of ions. So we know what ions are. They're those elements that have a differing number of electrons than protons. And in the case of cations, these are positively charged ions. And what that means is that we have more protons than electrons. And what we observe, as we see off to the right, where in red we have the ion and in gray we have the neutral element, is that cations are going to be smaller than the neutral atom. And what's happening here is that when we form a cation, what we're doing is we are removing electrons. And so when we're looking at things like lithium, beryllium, and boron, you can see we're looking at the +1 for the alkali metals, the +2 for the alkaline earth metals, and then +3 for things like boron and aluminum. And in this case, what we're doing is we're actually moving to the nearest noble gas configuration. And when we do that, we are removing all of our electrons from that valence shell. So we remove all electrons from valence shell. And this is when we're looking at our main group elements. We're not talking about our noble gases. And when we do that, we are effectively moving one electron shell in. So we're going to a lower, what we're saying here is we're going to a lower n value. So the new largest orbital has a smaller quantum number n. And so we can illustrate this with lithium. We know when we talked about lithium, it has the electron configuration of helium 2s1, which is the same as saying 1s2, 2s1. When you go to lithium plus, you lose that, so you just have the electron configuration of helium, which is the same as 1s2. So you can see that initially, our valence electron was in the n equals 2 level, and then after ion formation, we're now in the n equals 1 level. And when we do this, what we observe is that now we have a Z effective that is greater on valence electrons since we have less shielding of that highly positive nucleus. And we know for neutral lithium, it has a Z equals 3. And because it has that noble gas configuration of helium, 2s1, the number of shielding electrons is the number of electrons that helium contains. So I'd say this is the number of core or shielding electrons, and that's 2. So S is equal to 2. So for lithium, its Z effective is just going to be 3 minus 2, so that's only a +1. If we look at lithium plus, that just has the configuration 1s2, and so its Z value is the same. Lithium still has 3 protons, but now we don't have any core electrons because the only electrons are in the 1s orbital, so there's no shielding. So in this case, now we have a Z effective of 3 minus 0, so you have +3. And so those new valence electrons in the 1s orbital are getting to feel that full nuclear charge. And so, in short, what we can say is that removing an electron from the atom reduces its size. And where we have a reduction in size for our cations, we're going to be observing the exact opposite for our anions. And so in gray is the neutral atom, and in green is the ion. And you can see that in this case, we're adding enough electrons to reach the noble gas configuration for the ion. And as you can see to the right, what we are observing is that the anion is larger than the neutral atom. And so when we add that electron, it being a negative charge, it causes a little bit more repulsion in the largest orbital. And so while we're not looking at shielding here per se, we are just thinking about adding more and more negative charge here without changing anything about the nucleus. You can imagine you just have more things in the same area. And because they're similarly charged, they're just repulsing each other. And so if we look at our configuration for chlorine, that has the noble gas configuration of neon, and then you have 3s2, 3p5, and then for chlorine minus, you just have neon, 3s2, 3p6, And effectively, all that's going on here is now that you have 6 electrons in that p orbital, what they're doing is that they're doing a little bit more electron-electron repulsion. So you just have some extra electron-electron repulsion, and that just slightly expands the size of the orbital. And the reason that, when we looked at going across a row when you had your neutral elements is that we have no increase in positive charge, or another way to say this, no increase in positive charge of nucleus to valence. Or another way to say this is that there's no increase in Z effective. Z effective hasn't changed as we go from left to right here, and so we're not able to pull in that additional electron any further. And so, in short, what we can say here is that adding an electron increases the size of an atom. And so there's one more interesting thing that we can talk about with ions, and this is the idea of comparing the ionic radius of so-called isoelectronic species. And here, electronic just means electrons, and then iso is going to just be equal to the same number of electrons. And so, by definition, species with the same number of electrons are said to be isoelectronic. And so we're going to look at a series of isoelectronic species and see how their sizes compare. And so, in this case, we can calculate the number of electrons for each. We see oxygen as element number 8. And because it has that 2- charge, that means we have 2 more of our negative particle electrons than protons. So we have 2 here. Fluorine is element number 9. It has 1 extra electron. Sodium is element number 11. And because it has a positive charge, it has lost an electron in order to gain that. So we subtract 1. Magnesium is element number 12. We subtract 2 because of the 2+ charge. Aluminum, element number 13, we subtract 3. And so what we would see is that each one of these has exactly 10 electrons. And then if we look at the number of protons each of them have, we just look at their atomic number. So for oxygen it's 8, fluorine is 9, sodium is 11, magnesium 12, and aluminum 13. And what we'll see here is that the radius for each of these is going to go from, in our case, large for our anions. So we have these two right here, 133 picometers for oxygen, 140 for fluorine. And then for sodium, we have 102 picometers. For magnesium, it's 72 picometers. And for aluminum, we have 54 picometers. And so what we're seeing is that for these positively charged cations, which I'll highlight in yellow, as we go from left to right, we have the same exact number of electrons, but we have an increasing positively charged nucleus. And so you have this larger positive charge, and that gives you a smaller cation. And then for our anions, the oxygen and the fluorine, which I'll highlight in blue, what we see there is that the larger the negative charge, or large negative charges will give you large anions. And this is true for these isoelectronic species. So actually, I made an error here. So actually, these should be switched. So this should make a little bit more sense. For oxygen, its radius is actually 140 picometers, and fluorine is 133 picometers. So now it should work with what we have below, saying that the larger the negative charge, oxygen having that largest negative charge, the larger the anion. And so for our isoelectronic species, we'll go from highest positive charge when we're ranking them in terms of size to highest negative charge. And so if we talk about their size, what we'll say is that aluminum is smaller than magnesium, is smaller than sodium, is smaller than fluorine, is smaller than oxygen in terms of its ionic size. And if you want to look at an illustrative example, here we are right here, where we have oxygen sitting at 140 picometers, fluorine 133, sodium 102, magnesium 72, and aluminum 54. And in this case, we've switched the colors where the colored version is the size of the neutral atom, and then in gray is the size of the ion. And so we maintain that same trend in the size of our atoms. So the big takeaway is when ranking size of isoelectronic species, positive cations are smaller and negative anions are larger. And the more positive you are, the smaller. So more pos is smaller. And then the larger the negative. So larger negative is bigger. And that's the big takeaway here. If you want to dig down deep into the weeds, you can also think about the Z effective. Because for each one of these species that are isoelectronic with 10 electrons, technically their noble gas configuration will be, something, they all reach that of neon. So they should have 1s2, 2s2, 2p6. And if we're going to talk about core electrons, if these right here are valence, then what we have interior is going to be our core. So you have 2 core electrons, and then you'd have 8 valence electrons. And if we talk about the Z effective, what we would see is for O2 minus, it has, we have our Z value, we'll put our S, and we'll put our Z effective right here. So we have O2 minus, F minus, Na plus, Mg2 plus, and Al3 plus. They all have the same number of shielding electrons. That's those 2 that are coming from the helium designation. So 2, 2, 2, 2, 2. You can write down the number of protons they each have, 8, 9, 11, 12, and 13. And if you go ahead and calculate the Z effective, what you'd see for oxygen is that, the actual number of electrons now is 10 total electrons, but the Z effective felt by those on the outer edge is +6. So same as before, fluorine is +7. For now, sodium, it's +9, magnesium is +10, and aluminum is +11. So what we're seeing as we go from left to right is that the 8 valence electrons that each one of these have, 8 valence E minus that each species has, feel more positive pull from nucleus as we go left to right. So as you go towards these cations, the electrons feel more of that pull. And what that means is that they're going to start to contract more and more, just like we talked about with our atomic radius. And so in the next presentation, we're just going to talk about one other periodic trend, but this is the bulkiest one, so I wanted to spend a isolated video on this.